So if you look at most aerospace jobs in the field of control, guidance, and navigation, you will notice that a lot of these jobs require a proficiency in using Simulink and MATLAB. Now, as an engineering student, I'm pretty sure you all know what MATLAB is, but what is Simulink per se? This video will be an introduction to Simulink. So Simulink is nothing other than an add-on to MATLAB. It's used for control system design, modeling, and simulation. You need to know the software very well if you wish to work in the aerospace industry, especially in the field of avionics or guidance, navigation, and control, called G, N, and C, to build control systems for aerospace vehicles such as missiles, rockets, and jets. And also if you have an interest in flight simulation, because Simulink can be connected with external flight simulators such as Flight Gear and X-Plane. So it is a very powerful tool. Some applications for Simulink, there's many and many, but some here include the NASA Space Launch System flight control design, the Lockheed Martin Orion crew vehicle, and also the control design for the 777X. Now Simulink has been used for decades, but these are just some examples here. For our video, we'll be looking at a basic simulation of planetary entry and descent. It's basically a spacecraft coming back to the atmosphere. The variables include the position, the gravity, the force, and the mass. And these equations of motion can be obtained from the paper, which is linked in the description below. So these are two ordinary differential equations, and they can be used in Simulink to solve the problem. We also have some constraints, such as the initial height of 10 kilometers, full mass of 25, empty mass of 15, which means that we have fuel of 10 kilograms. The force input is 10, and it's inputted by a joystick action. The Simulink tools which we will use in this tutorial are the very basic tools which you all must know, because these are fundamentals, and they include PID control design, mathematical operators, input signals, output functions, math functions, and also the basics of ODE solving and integration. So let's jump into it. So guys, we are now in Simulink and we can start. And to open Simulink, you simply go into the MATLAB workspace and either type in Simulink and press enter, or you can also click this library browser here. So when you open up Simulink, you will have this window here. And based on your installation, you will have either all these block sets or you will just have this basic Simulink. For our purposes, we'll be just looking at the basic functions. So let's begin our problem. Let's first drag in the input. To zoom in, you simply move the mouse wheel up. We have force of 10, so double click on the block and set the final value to 10. So the force is being applied over a period of 5 seconds. Next, we can drag in our controller for the force input. So drag in a PID controller block here, along with the transfer function. For PID control, we just have KP and KI. So set these both to 1. It's only a PI controller. And for the transfer function, we just have BS plus K. So damping is set to 2 and spring is set to 1. This is a function of 10 to the orders of magnitude. So if I have something like 5, 5, and 5, it'll be 5s squared plus 5s plus 1. So here it'll be just 2s plus 1, as you can see there. Next, you also have a sum input. So we can set it up over here. Also, if you want to connect two blocks, you simply click and drag it like so. So we have our input over here. Next, we need to add a gain. So, and what is a gain? A gain is like an amplifier. And what that does is it simply multiplies the power of the signal by the value. So in this case, if I have a gain of 5, it'll multiply the signal power by 5. I'm just going to put -2 now, and it's negative because the force and the g-force are opposing. Next, you have an integrator. Now keep in mind that we're solving our second equation, as I mentioned before, which says m dot is equal to the force. Now the reason why I'm doing that is because we need to solve for the mass, and that goes into equation 1, right? So we need to do that in this manner. So let's set the mass. We had a mass of initial of 25 kilograms, and then it drops down to 15, which is the empty weight. So you put 25 in here and limit the output and put 15 as the lower saturation limit. So that means that it will not go below 15. Next, we can drag in a math operator. So go into math operations and drag in divide. Also drag in an add. So let's move this add here. To rotate a block, press Ctrl R. Okay, so now we need to set up this equation, right? Now we have mass here. We basically solved for the mass. It became from m dot to m. Up until this point, we have m dot is equal to u. All this here is u, and then it becomes m. Okay, so we have mass being divided, so drag in this over here. And it's u over m, right? So we have u going into this block here. Bring this addition down. Move this up here. And also let's drag in a constant value. The constant is for any constant value that does not change, and you can simply drag it in like so. And if you guys can take a guess, this constant will be the g-force, which is 9.81. Okay, so now let's do a recap. So what do we have here? We have a problem being set up by solving the second equation first and then feeding it into the first equation. This here is the second equation. We have m dot is equal to u, and we take an integral of m dot to get m, which is the mass. We have mass being divided by the force, u over m. So u is all this, and it'll go into the division block, so it'll be u over m here. And then we have g being added, so equation 1 is r double dot is equal to u over m plus g. And we have this here. So if you guys know, this whole thing is equal to r double dot, right? Because we have u, equation 1, and then being added to g to set up equation 2. Okay, so now we need some more integrations. So let's drag in a couple more integrations. And I've said couple because we need r from r double dot. So to click and copy a block, just right click and drag it. So what's this going to do? We have r double dot here. This block will do r double dot to r dot. And then this block over here will do r dot is equal to r. If we drag in another block, it'll assume that this is equal to r triple dot. So keep that in mind. Connect these two. And also we need to do something else. We need to set up the initial condition of the height, because we had height as 10,000 meters. So double click on this and set this simply to 10,000. Instead of limiting the output, we're going to be doing something else. So hit apply and then hit OK. So if you look at the paper in the description, it actually treats G as positive down. And we need to change this because our goal is to track the altitude. So to do that, you need to drag in a math function. Now this is very interesting because Simulink actually lets you define mathematical functions of any value. So you can take an input and find its cosine, find its sine, do some trigonometry to it, anything you want. So let's drag in this here. Or actually we can type in function and let's see what we get here. So we have a bunch of options here. So we need to use this function f of u, and u is an input. This lets us define a user-defined function, as you can see there in the block. So click and drag this one, Control R, and change it to 20,000 minus u, because our goal is to get the net altitude, right? So if we had 10,000 meters and it becomes 10,600, it means that we have dropped in 400. So we need to do 20,000 minus u. Hit apply, hit OK. So now we are almost done. We've essentially solved for what we need to solve for, which is the position. Simply drag this in here. And we can stop the simulation in an interesting manner. So our goal is to stop the simulation when the satellite hits the ground. That means that when the r is equal to 0, there's a function called compare to constant or compare to 0. So drag this in here and also search for a stop. So stop, stop simulation. So what this is saying is that when the position hits 0, the simulation will terminate. Let's first compile it. So if you want to compile a simulation, you simply click on this arrow here and you'll see that it's compiled. There's some more things we can look at. First off, we have the simulation time of 10 seconds. This can be anything you want. So I'm going to set it for about 35 seconds for now. Okay. Next, we also have this ODE 4.5. And I have a video which explains ODE 4.5. It is simply a numerical method in order to solve a differential equation. So we can do some more stuff. We can drag in a display. So we can see here our altitude now is 3.7 kilometers in a time of 35 seconds. So it basically dropped from 10,000 to 3.7k. If you want to see this in graph form, you simply drag in a scope. A scope tells you the output in real time. And press play. And you can see how it has dropped from 10,000 all the way to our altitude here in about 35 seconds. In the paper, it showed a parabolic trajectory, and we have something similar, which means that the simulation is considered accurate. Simulink lets you view signals in any manner you want, and if you want to view multiple signals at once, you use something called a multiplexer or a mux block. You drag this in here, you hit Control R, and you can connect any inputs you want, and you can see them all at the same time. To show you what I mean, let's do this. Let's also see the mass as a function of time. And if you run this, we have two values. Okay, the first one is the altitude, because we have this R going into here, and it's sequential, right? And the second one is the mass. Next, we can also change simulation time to about 45 seconds. And it drops to this value here. Now what's going on is that Simulink has a built-in inaccuracy, and it won't be exactly 0, right? Because if you look at an ODE solver, it won't stop at 0. If you want it to stop at a value is equal to 0, it's going to solve it by step. And when the next step goes below 0, it's going to stop. So what this is saying is that it's actually stopping at a value close to 0, something to the power of -10. And if you go any step below, it'll go below 0. So it's going to stop the simulation. So guys, thank you for watching. This video covered a basic introduction to Simulink. And I have videos on my channel which also delve into Simulink and cover more intricate topics like control design, flight simulation, and aerospace applications. My name is Vinayak. I welcome you to VDEngineering. The goal of the VDEngineering channel is to spread videos and educate the world on aerospace engineering simulations, tutorials, and science. My channel covers videos based on MATLAB simulations, rocket propulsion, and also flight simulations and fluid mechanics for aerospace applications. This channel's goal is to spread aerospace engineering around the world and to promote more students to study it, mainly because there is a big demand in aerospace field nowadays since technology is always changing. And thank you guys for watching. With that being said, I'll see you guys in the next video. Take care. Have a nice day. Bye-bye.